Hello everyone! Today, I would like to present the introduction of our group project. In this project, we focus on the application of a first-order differential equation to model the total population in Bulgaria from the year 2000 until 2024. Based on the data, by the end of 2024, the population of Bulgaria is recorded at 6,757,689. This study is based on the Malthusian model, which was introduced by Thomas Malthus in 1789. This model is widely used to analyze human population dynamics. According to the Malthusian model, the rate of change of a population is proportional to the population size at that time. This relationship can be written as dP over dt equals to Kp, where P of t represents the population at time t and K is a constant.
First, we define Pt as the population at time t, where t is measured in years. Based on the assumption that the rate of the population's change is proportional to the population size, we use the differential equation, which is dP over dt equals to Kp, where K is a constant. And then, to solve this, we separate the variables and integrate both sides. After integration, we obtain the general solution, which is P equals to AE to the power of KT, which A is a constant. Next, we apply the initial conditions where T equals to 0, which represent the year 2000. The population is 8,520,000. So next, we apply the initial conditions when T equals to 0, which represents the year 2000. The population is 8,520,000. Substituting this value, we find that A equal to 8,520,000. So, the model becomes B equal to 8,520,000 e to the power of Kt. Then, we determine the value of K using the population's data from the year 2001. By substituting these values into the equation, we calculate K is equal to the negative 0.00904873. Since K is negative, this shows that the population is decreasing over time. So, the final model is P equals to 8,520,000 e to the power of negative 0.00904873 p.
Next, in Table 2, we compare the actual population data with the estimated values. The estimated data closely follows the actual data, which suggests that the model used is reasonably accurate in predicting the population trend. Although there are slight differences between the actual and estimated values, the overall pattern remains similar. In conclusion, both tables show a clear downward trend in Bulgaria's population over the 24-year period, and the estimation model effectively represents this trend.
The result obtained from this project demonstrates that first-order differential equations. Based on the model, the population of Bulgaria was analyzed from 2000 to 2025. The negative value of the constant indicates that the population is undergoing exponential decay rather than growth. The decreasing trend in the population of Bulgaria may be influenced by several real-world factors such as low birth rates, aging population, immigration, and economic condition. Therefore, while the model provides a good approximation of the general trend, it may not fully capture all fluctuations in the actual population data. Furthermore, the model assumes that the rate of decay remains constant over time. In reality, population exchange are rarely perfectly exponential, as factors such as improvements in healthcare or changes in economic stability can alter the rate. This means that the accuracy of the model is higher over shorter periods, but may decrease when applied over longer durations. Here we can see the actual population of Bulgaria from 2000 to 2022. The graph shows a steady decrease over time, indicating that the population has been consistently declining. This downward trend suggests factors such as low birth rates, agree. Aging population and immigration are affecting the country. This graph shows that the particular solution of the population change over time is based on the mathematical model. The smooth curve highlights an exponential decay pattern, meaning that the population is decreasing at a rate proportional to its size. In this slide, we use our model to predict population values for different years. First, we substitute t equals -10 to estimate the population in 1990. The model gives a value of about 8.76 million. When we compare this to the actual population, we can see that the model is slightly underestimates the real value. Next, we substitute t equals 20 to predict the population in 2020. The model gives approximately 6.68 million, which is very close to the actual data, but again shows a small underestimation. This result shows that while the model is reasonably accurate, it does not perfectly match real-world data due to simplifying assumptions such as a constant rate of decay. In this graph, we compare the actual population data with the estimated value from the model. The two sets of data are quite close, which shows that the model provides a good approximation of the real population trend. However, there are a small difference because real-world factors are not perfectly constant.
Alright, for this slide, I'm going to explain how we calculate the percentage area from two values. First, we identify the actual value, which is, and the reference value, which is. Next, we use the percentage change formula, which the actual value minus the reference value divided by the reference value, and multiply it by 100%. So, we subtract the value off from the value, then divide it by. After calculating, we get approximately 1.738%. This means there is a 1.738% decrease from the reference value to the actual value, since the actual value is smaller. So overall, this shows that the value has slightly decreased about 1.7%. The percentage error is 1.7% because the predicted value and the actual value are very close. The difference between them is small, so the error is also small. This means the model is quite accurate. The small error happens because the model is only an approximation and the data may vary slightly.
In conclusion, this project shows how a first-order differential equation can be used to model real-world population changes. We assume that the rate of change of population is proportional to the population itself, which led us to form the equation dp over dt equals to kp. By solving it using separation of variables, we obtain the exponential model p equals to ae power of kt. Next, by substituting actual data from the year 2000 and 2001, we were able to determine the constant A and K. The value of K was negative, which indicates that the population is decreasing over time. This result matched the real population trend in Bulgaria, where the number of people has been gradually declining. So, our model fits the data quite well. However, this project highlights how mathematical modeling helps us understand real-world situations and make informed prediction about the future. Thank you.